Welcome back to my course Aspects of Biochemical Engineering. In the last couple of lectures, I tried to concentrate on the reactor analysis, and this coming two lectures, today's this lecture and coming lecture also, I will talk more on the reactor analysis, because I consider that this is very important for the reactor analysis, because I initially I pointed out, you can remember that the one of the major objective of this particular course to develop the expertise, that to get a desired amount of product, what should be the volume of the reactor. So, until unless you do the reactor analysis properly, you cannot find out what will be the volume required for getting a desired amount of product. Now, in the last lecture, you can remember that I tried to explain this continuous start tank reactor and the plug flow reactor in details, and try to find out that how you can calculate the conversion efficiency of the in the CSTR as well as in the plug flow reactor, and also how you can find out the volume of the plug flow reactor that and continuous start tank reactor. Now, this particular lecture I try to concentrate on two different aspects. One is the batch process, that how you can analyze the batch process, and second also I want to try to analyze the reversible reaction in the batch process, that how you can analyze the reversible reaction. So, these are the couple of things I want to take care in this lecture. Now, if you look at the first problem that we have, that this problem says that in the homogeneous catalyst of a chemical of given concentration, aqueous reactant A is converted to product at the following rates, and CH alone determines this rate. So, you know that what I want to know at different Ca value, that is 1, 2, 4, 6, 7, 9 and 12, what is the rate of the reactions. This in a particular CSTR, that in a batch process, that they find out that what is the different rates. We plan to run the reaction in a batch reactor at the same catalyst concentration used in getting the above data. Find the time needed to lower the concentration of A from Ca0 10 moles per liter to 2 moles per liter. So, this is this problem if you look at this problem. So, we know T batch minus dCA this will be minus RA, am I right? Minus RA. So, this is Ca0 to Ca. So, in this problem, what is happening, they have given different value of Ca, and at the same time they also given different value of the rate equation that is given there. So, from that we shall have to find out time of the batch process. Now, how you can do that? That we can do it very easily, that this is equal to minus RA. So, if we plot 1 by minus RA versus Ca, we will get some plot like this, or this way or that way, whatever is there. Now, if you know the Ca0 value here, and if you know how much of the Ca should be converted, then area under this curve you can find out the volume of the the time required for the batch process. This you can easily find out. Now, how you can calculate the area, that is very important. So, what I can do, I can make a straight line here. So, if you look at this is what, this is a rectangle, and what is the area of rectangle? Is length versus breadth. Am I right? This is length, this is breadth. So, if you multiply that, you will get the area. Now, you can put a straight line here. So, if you straight line, then you will find a triangle. What is the area of a triangle? Half base into altitude. So, you can do this, and some portion will be remaining, that you can find out what the different squares. One square, if you know that what is the value of one square, if you calculate the number of squares, from that you can find out that total time required for that, and that gives you the idea of the time required for a batch process. So, in this problem, that what is given, in this problem what is giving, Ca0 is 10 moles per liter and CaF is 2 moles per liter. Am I right? And the batch as I showed you, the batch time, that is we calculated like this, dCA by minus Ra, and Ca0 to CaF that we have. Now, the integration can be evaluated by the graphical method or by numerical methods. Area under the curve, Ca versus 1 by minus Ra between Ca0 to CaF. Let us see how we have done that. So, this is we calculated in this problem, we have the values of Ca value is given, Ra value is given, but we shall have to convert it to 1 minus Ra, because that will reverse, because your plot is what? Plot is minus Ra by Ca. Because why? Because T batch is equal to minus dCA by minus Ra. Am I right? So, this is 1 by Ra and this is Ca. So, you can until unless you 1 by Ra, you cannot draw this graph. Now, if we plot 1 by minus Ra, this is, you can see minus Ra is there, and this is Ca. So, we have this kind of plots. So, so in this problem, if you look at the problem is that we shall have to reduce that 10 moles per liter to 2 moles per liter. Am I right? So, in this problem, that so this is 10 moles per liter and this is 2 moles per liter. So, area, so this is the curve that we have, and area under this curve you have to calculate. Now, question comes, how you can do that? You can do this very easily, that if you can consider this as a triangle, then you can consider from here to here, you can consider as a rectangle, then here you can consider as again triangle, again you can rectangle, like this you can do that, and here you can do that, you can do that. So, you can calculate the area under this curve, maybe 1, 2, 3, 4, 5, 6, and then you find out the T batch, what is the time that you required in the batch process. So, it is coming, it will come around the 22.416 hours, that from the graph we can find out this particular results. Now, let me go to the second very interesting problem, that is the what you call reversible reaction. And in the reversible reaction, we know that we have forward reaction and the backward reaction. The BPS reaction, we assume this is irreversible, and this is the reversible reaction we have. And in this reversible reaction, two things is very important. One is equilibrium condition and the normal condition, normal operating condition. And I told you here, I want to highlight again that at equilibrium conditions, that equilibrium, we have the equilibrium constant, we call it equilibrium constant, and equilibrium constant equal to what? Concentration of product by concentration of substrate. Am I right? Now, this is the concentration of product, this is the concentration of substrate. Now, I told you that when you work with any kind of reversible process, to increase the product concentration, either you have to take the product out, so that more substrate will convert to products, or you have to add more substrate, you can get the product. So, let us see that how we can analyze this system. Now, this is a plug flow reactor, a plug flow reactor of capacity 2 cubic meter. 2 cubic meter means what? 2 cubic meter means 2000 liters. Am I right? The process and aqueous flow rate is, what is the flow rate is there? F is equal to 100 liter per minute. Containing the reactant, CA0 value is given. This is equal to 0.1 mole per liter. This reaction is reversible and represented by this, and the equation is minus R A is equal to 0.04 into Ca. So I want to write it here. This is suppose the K1 and this is K minus 1. Sorry, the sign is given in different way. So let us assume this is K1 and this is backward is K minus 1. The K1 is 0.04 and K minus 1 is 0.01. This I want to highlight. This is how we can the first find the equilibrium conversion, and then find the actual conversion of A in the reactor. So, two things we shall have to find out in this particular problem. What is the equilibrium condition? That means, under equilibrium condition, what is the percentage of substrate that is converted, and what is the actual substrate converted in this reactor. Both the portion that we shall have to solve in this particular problem, and by the reactor that we are considering is the plug flow reactor, and we know the plug flow reactor expression and the batch reactor expression is same, because same integration, that tau CSTR tau plug flow reactor is what? Minus dCA by minus RA. Am I right? And also this is equal to same as T batch. So, this is similar type of expression that we have. Now, as I pointed out before, that let me tell you again, that when you solve any kind of problem, first please write down what are the things that is given in the problem. So, K1 value, we can rate equation, we can find out K1 equal to 0.04 minute inverse and K2 is 0.01 minute inverse. Ca0 we can easily calculate, find out how much is mole per liter. Cp0 is 0. Cp0 means at the 0 hour the product concentration is 0, and flow rate is 100 liter per minute, and plug flow volume of plug flow reactor is 2 cubic meter, that means about 2000 liters. Now, M is the ratio of Cp0 by Ca, that is equal to 0, because at the initial point at 0 hour this product concentration is 0. So, M should be equal to 0. So, this is the input of the problem that we have, and from that we can find out that what is the equilibrium conversion that we have in this particular process. Now, if you go back to our expression, that when we discuss the reaction kinetics, then we discuss the reversible reaction in details, and there we can find out that K1, what is K1? K1 is the rate constant of the forward reaction, because if we write like this is K1 and this is K2. This is K2 for the backward reaction, K1 for the forward reaction. Now, if you take the ratio K1 by K2, this is equal to m plus x AE. What is the AE? X AE is the fraction of A that is converted under equilibrium conditions. That is called x. E stands for equilibrium conditions, and 1 minus x more x into AE. This expression we have seen, we have during this analysis of reversible reaction, we have shown this expression. Please refer this. And then in this problem we know the value of K1, we know the value of K2, this m value is 0. So, we can easily calculate the value of XAE, and this is coming about 0.8. That means, equilibrium conversion of this process is 80%. Equilibrium conversion, because again I am telling you that what do you mean by equilibrium conversion here. Suppose A, B, K1 and K2. So, if you look at minus dCA by dt, this will be equal to K1 into Ca if you consider first order kinetics, K2 into Cv. Now, under equilibrium condition, this should be equal to 0. So, I can write K1 into Ca equal to K2 into Cv. I can easily write. So, K1 by K2 equal to Cv by Ca. This is equal to constant, equilibrium constant. Am I right? This is what is written there. Cv equal to this, and Ca if we consider, then we can write this one. So, we can put the equilibrium condition here. Then we can put this. Then we can calculate the value of XAE, and that is about 80%. Now, next is that next problem is that let me go through that what I told you, that in the next problem we shall have to find out the actual conversion of A in the reactor, that you have to find out. Now, let us see how we can do that. Now, this is the rate equation that we have, because I have already done that. This is equal to what I showed you, minus dCA by dt equal to K into Ca minus K1 into Ca, K2 into Cb. Am I right? The K1 equal to what? K1 equal to Ca0 into 1 minus Xa, and Cb equal to Ca0 into Xa, because we considered Cb0 equal to 0. So, if you consider that is like this. So, now tau CSTR equal to Ca0 into Xa minus Rxa. Now, putting all the known values in the above equation and solving the trial error method, that we can find out the value of Xa. Now, that that in this problem that we shall have to we have here, you can see that we have this is the CSTR volume, and this is the flow rate, aqueous flow rate. So, from that we can easily find out the volume of tau CSTR, that you can calculate the tau CSTR. Then if you know the tau CSTR and Xa0 value know, so the Xa value you assume trial error method and find out under what circumstances the left hand side is equal to right hand side. And if you do that, you will find that when Xa equal to 0.4, then left hand side will be equal to right hand side, and since it is 0.4, that means actual conversion is about 40% that take place. Now, let me go for the third problem that we have. This is the aqueous decomposition of A is studied in an experimental mixed flow reactor. Now, here I want to tell you one thing, that CSTR can be we can express in different way. We can, though it is says that CSTR may continuous start tank reactor, sometimes we call it mixed flow reactor. Also, when it is used in the biological system, we call it chemostat. So, basically all are CSTR, continuous start tank reactor. So, different name we put for the CSTR, because one is mixed flow reactor or chemostat when we use in the biological process, and in the chemical process mostly we use either CSTR or mixed flow reactor. So, this is the mixed flow reactor, and we mentioned that is CSTR. The results in table are obtained at the steady state run, and steady state run means here let me show you one thing, that suppose this is CSTR. Okay. Now, there is a flow, this is inflow, that is outflow, and I told you this flow rate should be same. Well, why should be same? Because if F is differ, either volume will increase or decrease in the reactor. So, F should be same, because we want to maintain the same volume in the liquid volume in the reactor. Liquid volume is the working volume. Liquid volume is considered as the working volume of the reactor, because we assume the reaction take place only in the liquid phase. And what I told, suppose you want to carry out a reaction A to B, and you want to carry out in this reaction. So, what we shall have to do? We shall have to first you have to run this process in the batch mode, let the reaction take place when it is maximum, then you book the flow rate. Now, as soon as you give the flow rate, that here you have Ca0, am I right? And this is here Ca. Now, if you look at that concentration, that with respect to time, and that concentration of Ca, it may little bit change with respect to time. This is outgoing Ca concentration will be changed, a time will come, it is constant, and when it will be constant, then we call it steady state condition. So, in this problem they are talking about, and it requires some time. This is the time required for to attain the steady state conditions. So, this is exactly what it is mentioned here, that the runs of the table are obtained in steady state run. To obtain that 75% conversion of the reactor in the feed stream 0.8 moles, what holding time is required in a plug flow reactor. So, so that is the 75% of this means that is Ca0. Suppose it is 0.8 mole per liter, then if you consider the 75%, how much will be remaining? That is 1/4. Am I right? So, Ca will be 0.8 into 1/4, that is 0.2 mole per liter. This is mole per liter. Am I right? So, you have to find out that to obtain 75% conversion of the reactant, what holding time is required in the. So, we shall have to find out tau plug flow reactor. Tau plug flow reactor we shall have to find out in this. So, so in this problem what is given? In this problem in this problem we operate CSTR at different substrate concentration, and different you see that in this problem that in the feed stream you have this, in the exit stream is this. So, this is given there in the feed stream, and exit stream is like this, and holding time is like this. Now, one thing I want to point out in the as per the CSTR is concerned, that in the CSTR when you calculate tau CSTR equal to Ca0 minus Ca by minus Rd. Am I right? So, you can, the feed stream is there and this is there. So, time is required. So, you can find out already, you can find out the minus Rd value. You can find out at different substrate concentration, you can calculate the minus Rd value. This is, and what is the substrate concentration you have to assume? You have to assume this, because I told you under steady state conditions substrate concentration remain unchanged. So, this is the, so at different substrate concentration what is the Rd value is given. Now, once you have that, So, CA0 value is there 75% conversion. So, what I told you that CA should be about 0.2 mole per liter, am I right? And CSTR is like this. So, this is the things that we have. This already we know this. This is minus RA for the CSTR, we know that. Now, we can easily find out CA value at different CA value. What is the 1 by RA? First we calculate RA value, then we calculate the 1 by RA value. So, this we can have that. Now, we know the plug flow reactor, when you tau plug flow reactor is equal to minus dCA by minus RA, am I right? So, now here you can again plot minus 1 by RA into CA, and that CA that I do not know what kind of plot you have to find out, and suppose this is 0.8 mole per liter and this should be 0.2 mole per liter. So, you have to find out area under this curve. So, you can find out the value of tau plug flow reactor. This is how you can calculate. Now, this is the equation, this is CA value you can calculate, and this is about 0.2 I showed you, and then we when we calculate this area under this curve, when we calculate 1 by RA versus CA, that we can find out this is tau plug flow reactor, and this is coming about 300 seconds. So, you can easily calculate. So, this problem I considered very interesting problem in the sense that how the batch data can be utilized for finding out the time required for the operation of the plug flow reactor, because when you operate a continuous start tank reactor, then you find after infinite time, when the steady state condition reach, your substrate concentration remain constant. At that particular concentration, what is the rate of reaction is there, you can easily find it out from this equation tau CSTR equal to CA0 minus CA by minus RA. So, if you know that, so different CA value you can give the RA value, and if you know the RA value you can find out minus 1 by RA value, and if you then you plot minus 1 by RA value by CA, the area under this curve will give you the value of tau plug flow reactor. So, this is how you can find out. Here you can see that this is the kind of curve we got, and this is 0.8 and this is 0.2. The area under this curve you can find out that this is what we call tau plug flow reactor. So, what we learned from this particular lecture, we learned that how to find out the batch time, and I told you that to find out the batch time, either you go for numerical techniques or computational techniques, or better you go for the kind of graphical analysis. And since the batch time is equal to minus dCA by minus RA, so if you plot 1 by minus RA by CA, and area under this curve we can easily calculate and find out that for the conversion it's 75%, 80%, 90% substrate conversion, how much time is required, you can easily calculate. Now, in case of reversible reaction, we come across two things. One is what is the equilibrium the conversion, with that equilibrium condition, what is the percentage conversion of the substrate, how we can calculate, and also in the normal reversible reaction at time t, what will be the conversion that we have. But only in case of reversible reaction, I told you that two strategy we maintain to increase the product formation in the reactor. Either as soon as the product form, if you take it out, more substrate will convert it to product, or you add more substrate in the reactor so that you will get more product in the reactor. Now, the last problem is very interesting, how I try to find out how from the data of the CSTR can be utilized for the operation of block flow reactor. Thank you very much.